Good. Now, hopefully this is working today, and that I don't get done with the entire lesson and realize I didn't record. Okay. So, pretty simple concept today that you've done already, and that is, well, we're going to cover two things. The first thing is transformations. Okay. The title is called New Functions from Old Functions, but it's basically taking our mother functions and changing them being stretching them, shrinking them, which is nearly as important as the sliding left, right, up, or down, and refreshing your memory on how to do that. So when it comes to something like having to graph the square root of x minus 2 plus 3, you're able to do that by thinking about it in a mother function scenario there. Okay? We're also going to talk about domain and range of function. As we talked about the other day, I like doing domain and range problems by looking at graphs. Okay? Ideally, if you understand the transformations,
Slideshow. Over your shoulders, that's pretty good. All the day 3 we're on. Send that to Notability, you know how to do that. And then you got it for notes.
Okay. Domain and range based on a picture. If the function gets a lot more complicated, the domain and range can get more complicated, but if you can manage to sketch a picture of that graph, then the domain and range is a fairly easy problem. I would argue no matter how complicated of a picture I give all of you, you could tell me what the domain and range is. However, if I give you some ugly, nasty functions, you might struggle a little bit. All right, so I'm going to take a graphical approach to it and see how we do with that. We're going to talk about transformations, moving things around. We're going to talk about composite functions. What's a composite function?
I'm gonna give a gander.
Oh, beautiful.
Two functions together
How so?
with
I give you,
two variables.
okay, getting warmer.
Would it be like lost it there.
It's a good start though. It does involve two functions. Those functions have the same variable. Anybody else? Oh, well, this will be exciting then when we get to composite functions. I know you've done them, you just don't remember what they're called. And then we're going to talk a little bit more about the absolute value function. I hinted at it last class, but we're going to get into some a little bit more work with it with some pictures and stuff and show you how to handle the absolute value function. Then you should get excited for the pack assembly. Right?
Yes.
Cool.
It's on the field, right?
Is it?
Yes.
You have sunglasses. I figure out how I'm going to get my car and get my sunglasses before I go out on the field. Otherwise, I won't be able to see anything. All right, so here we go. Transformations. Let's start with a nice, easy mother function. In your notes, please draw a picture, a sketch, if you will, of the graph of the square root of x. By the way, is the square root of x a function? Yes. Why? Say, you talking, Dave?
That's the square from y-axis.
Correct. It does pass the vertical y-axis. We will use the square root of x as an example for a good chunk of the rest of the chapter because we'll talk about this, the graph of the square root of x versus the graph of the inverse that gives you something looking like the square root of x. That doesn't make any sense now. It will later when we talk about the inverse. Okay, so you got a picture, yes? We're good to go? What can you tell me about the picture of the square root of x, or the sketch of the square root of x? Describe it for me, Hannah. It's only positive, good, because you can't take the square root of a negative number because we're in the real number system. Outstanding. Anything else interesting about it? Good. Anything else? It passes through the origin. Very good. It should look something like that. One way to think of that is it's half of a sideways parabola. It can't be the full size sideways parabola, otherwise it wouldn't pass the vertical line test. Okay, good. So there's one of our mother functions, the square root of x. what happens when we start looking at the domain and range of that? Now, if I said to you, if we go back to this, and I said to you, Andrew, what's the domain and range of that? Could you do it without the graph?
You could.
Okay. What would be the things you would be concerned about?
But what do you mean, the limits of it? Like,
What would determine the domain of that function? How would you approach the problem without a picture, in other words?
well, there's no asymptotes and it's square root, so it could be a negative numbers. So.
Good. Okay. Playing off of what Hannah said before, it's got to be positive because
Yeah.
we can't take the square root of a negative number. So we would know that the domain would be 0 to infinity. Okay? Can't put a negative number in there. The range becomes a little trickier. So one way to think about it analytically is if I put in all these.
My bad.
Hi.
Hi.
Did you get lost?
I forgot about the
The whole class go to school thing?
yeah.
Or you sitting at Chick-fil-A?
I was sleeping actually.
At Chick-fil-A?
I wish not
Oh.
on my bed,
Oh.
but yeah, that's my bad.
I understand. No problem. I forget where it was.
Domain. Range.
Oh, domain range, yeah, getting the range. So the range can be a little tricky because you have to ask yourself, so if I'm only going to put in the numbers 0 to infinity, what kind of numbers get spit out? And that can be, in an easy function like this, is not too bad. When it gets uglier, it could be very challenging. So again, I like to go to the picture. And when I see the picture, the range becomes very clear. It's also 0 to infinity. The one chunk I'm missing from that picture that should technically have an arrowhead on it, but it doesn't. I have failed you. You know whose fault that is, right?
Everett.
That's correct. He didn't put the arrowhead on there. Okay, so domain and range. Question?
This might be a weird question.
It's not a weird question. The only question is, no, that's never mind.
Okay, well, I know, so to be a function, it can't have a negative half on the y-axis.
Correct.
But isn't technically the square root of anything to be positive or negative?
Good question. When you're solving an algebraic equation, so let's suppose I give you x squared equals 4. When you take the square root from an equation standpoint, you have to include both possibilities, plus or minus 2. When we're talking about a function scenario, we only consider the positive values because we want it to remain a function. If you included the negative part, then all of a sudden you have that sideways parabola that I talked about, and you can have a function.
Okay.
Okay, so we're cheating and forcing ourselves to stay with functions. Good. So again, hopefully if you get the transformations under control, the domain and range issue becomes pretty simple and straightforward because you just look at the picture. So let's suppose we took that mother function of the square root of x and I said to you, what would the graph of the square root of x minus 1 look like? Okay, so you could cheat, not even cheat. One way to do it is to get out your handy dandy graphic calculators, graph it and see what it looks like, but this is probably going to happen on the non-calculator portion of the AP test. You all knew that there was a non-calculator portion of the AP test, right? If you didn't, you do now. Half of the test is non-calculator. Okay. So the question, I go back to the original question. What does the minus 1 underneath the radical symbol do to the graph of the mother function?
Shifts it.
Slides it.
No, right. No,
Right.
it goes right.
You've covered every direction except up. So say up and then it's going to go up, right. So it's either going to go up, down, left, or right. That's not a false statement. Okay? She's right?
It goes to the right. So yes, she was.
Okay, good. Correct, it goes to the right. How do you remember that? The way I do it is, if the number is on the outside of the function, it's going to affect it vertically. If the number is inside the function, it's going to affect it horizontally. When you affect it horizontally, it does the opposite of what you think it should do. So I see that that negative 1 is inside the function. My immediate reaction, or the immediate reaction of somebody who doesn't know what they're talking about, might be, oh yeah, it's got to go to the left because that's the negative direction. But it's the opposite because it's inside the function. By the way, you'll notice I wised up after the whole mother function incident the other day There are certain things I have on my slideshow that you don't have. So you're gonna have to draw a sketch of that if you wanna complete your notes. Okay, so what's happening in the second one? What does h of x look like? Nadia, any idea what the minus sign or the plus 1 is gonna do to that bad boy?
The minus sign is gonna like invert it, like flip it the other direction.
Okay, we'll come back to that in a second. And what's the plus 1 gonna do?
Plus sign is gonna move it to the left.
Correct. Okay, so let's talk about that whole flipping thing. You are correct. The question is, what's it going to flip over? The x-axis? You got a 50-50 chance.
The y. The x-axis.
The x-axis, very good. Yes, it looks like that. Oh, now you're saying to yourself, self, which one happens first? Or does it matter in this case? So looking at that picture, that green graph, did I flip the function over the x-axis first, then slide it to the left 1? Or did I slide it to the left 1 and flip it over the x-axis?
Doesn't matter.
Doesn't matter in this case, correct. You're gonna get the same results. But which one happens first becomes relevant in some problems. The easy thing is, it always follows the order of operations. Start from the inside, work your way out. So technically speaking, that x plus 1 is in parentheses. You do the parentheses first. Please excuse my dear Aunt Sally. Move it to the left 1, flip it over the x-axis. Go ahead.
When does it flip over the y-axis?
Wouldn't it flip over the y-axis?
Yeah, what does it?
Oh, when does it? Very good. When the minus sign is inside the function. So if it was the square root of negative x. All right, so what happens in k? Patrick, what do you think?
You'll move to the right.
Good.
We move down.
Yes or no? Let's see what happens when I click. Outstanding. Which one happened first? Doesn't matter, correct, in this case it doesn't matter. Notice the second minus 1 is on the outside. When it's outside the function, it affects the vertical transformation there. Slides up or down, in this case down. So, I would repeat, I feel like I'm repeating myself, but I will make my point again. If I gave you k of x as a function and asked you for the domain and range, you might find that to be a challenging problem. However, when you see that blue picture in the bottom right-hand corner, I would argue that every one of you could easily tell me what the domain and range of that function is. Is that an accurate statement? Good. Okay, so we're not even going to bother with that question. Are we good? Beautiful. You'll notice in my picture, I didn't intentionally color the dots in red, but the question I would ask you is, should those dots be solid or open?
Solid.
Solid, because you can take the square root of 0. Very good. That won't always be the case in all functions. Please tell me this is review, yes? Outstanding. Okay, so transformations. You know, there's a quick summary of what the pictures look like when you change things. So in the first one on the left, you take that parabola, you slide it up. On the next picture, you take that parabola, slide it to the left. You flip it over the y-axis. The other one is, the reason I included this picture is because of the last picture there on the right. We've got a 1 minus the quantity of x plus 3 squared. So what's going on there? Well, it's being slid to the left 3, it's being moved up 1, and it's flipping. And the order that happens follows the order of operations. So you're going to slide it 3 units, you're going to flip it, and then you're going to move it up. So again, just follow the order of operations, you'll be fine. For those of you that want to see the calculus speak there, the fancy calculus terms, that's all the possible transformations. The first 4 after the original graph is easy. We've talked about that already. You know, if it's inside, minus moves it to the right. If it's inside and it's positive, it moves it to the left. Move it up, move it down. and then you've got your reflection things. We don't do a lot of reflections of the last two. We don't flip over the y-axis very often, and we don't flip over the origin very often. By the way, reflecting over the origin is the same thing as turning it over or flipping it over. So if you think of a graph of like x cubed looks the same as right side up as upside down because it's being reflected about the origin. Okay, we're good? Again, hopefully this is review. As we mentioned earlier, when Andrew was talking about finding the domain without the picture, there's two things we're concerned about. One is no zero denominators, ever. I shouldn't say ever. Very seldomly zero denominators. Way in the future, like April, we will take a look at the simple statement of 0 over 0. What does 0 over 0 equal? Okay,
Undefined,
why?
multiplied by 0.
One possible answer. Other answers? Danny?
1, because it's 0 over 0, and it's equal to 1.
Outstanding. Second possible answer. Chris?
Like infinity.
Why?
I just know that.
The math gods shined upon you and blessed you with the information that 0 over 0 is infinity. Third answer. Any others? What happens when the numerator of a fraction equals 0? What's the fraction equal?
0.
0. There are 4 possibilities. Which one's correct? All of them or none of them, and that's what we'll talk about later on. We need to do a whole bunch of work before we can intelligently discuss what 0 over 0 actually equals. Earlier in the whole mess, we'll talk about things like what is 3 over 0, what is 0 over 3, that kind of stuff. But the 0 over 0 thing we have to wait for a while. And then the second thing we already talked about is no negative square roots. Remember, you can take the cubic root of a negative number. You cannot take the square root, the square root of a negative number. Or the 4th root, or the 6th root, or the 8th root. Pregunta, señor.
So what you're saying about like those 4 things, how would one be ready for all that?
I could explain that to you, but your head would explode and you'd start to cry. Yeah, it doesn't seem right.
Because math only has one right answer.
Not always. Welcome to calculus.
Most of the time.
Okay, so let's suppose I have a dot, like in geometry,
Yeah.
a point. Point has no size, correct?
Correct.
So how many would fit in a little Dixie cup?
Trillions. Right.
Also known as
Infinity.
infinity. You with me? Okay, how many would fit in this room? The cup is in the room. I got points in the cup. Now I fill the room with points. How many points are in the room? With the points in the cup. Yes?
Yeah.
Which number is bigger? The number of points in the room or the number of points in the cup? They're the same. Does that make any sense?
Yeah.
Oh, no. The correct answer is it makes absolutely no sense.
I got it, no.
How can the amount of stuff, this isn't Harry Potter, how can the size of the tent on the inside be bigger than the size of the tent on the outside? How can I have more in the, how can I have the same amount in the cup as I do in the room? It doesn't make any sense. The human brain doesn't process infinity very well. Yeah, we just say it's calculus, and then we move on. So 0 over 0, calculus. Okay. By the way, don't use it on your quizzes and tests. If you get stuck on a question, don't just write calculus, and then, the emoji of the shrugging shoulders and think you're gonna get full credit on that. Half credit is good, not full credit. All right, Max, what can you tell me about that function? Anything interesting?
It's a fraction.
Outstanding. Also known as a rational function. Well done. What else you got for me?
Squared.
It is. Very good. What else?
I don't know.
What can't x be?
2.
Or?
Plus or minus 2. Negative 2.
Or negative 2. Right?
Yeah.
Good. Can it be anything else? Sorry, I said that wrong. Can it not be anything else is what I meant to say.
No.
No. So we're good, right?
Yeah.
So what does that tell you, the rest of you, what does that tell you about what happens at x equals 2 and x equals negative 2? Go for glass dose. Okay, we talked about that the other day. So what would the domain of that puppy be, Max? Well, there it is right there, sorry.
Infinity
Okay, and let me put it up so you can read it to me, go ahead.
to, negative infinity to negative 2,
Uh-huh,
and then negative 2 to 2,
uh-huh,
and then 2 to infinity.
right. That is a pain in the butt to write it. That's interval notation. What's the easier way to write that? X cannot be equal to positive or negative 2. And if you want to be all fancies in your fancies, you can say cannot be plus underline minus 2. Good. Okay. Max, we're coming back to you.
Alright.
So, we've established the domain. What's the range?
The what?
The range of that function?
Zero?
Can't be 0
Oh, wait.
or only 0?
Oh, no.
Not easy, right?
No.
Should we cheat?
Yeah.
Good. Get out your calculator, or do you have Desmos on your iPad?
No.
No. If you have Desmos on your iPad, use your iPad. If you don't, get out your calculator, grab that puppy,
I'm using Desmos.
and tell me what the range is from the picture.
Alphabetics.
Y cannot equal 0.
How would we solve this? What did you solve for?
So can you just write that on like a range?
Divided by.
I have it to X, so we
Oh,
just-
that's Tuesday.
Equally loaded.
I know you-
Oh, range, I got it. Where?
No, I'll always call you.
Let's see it, let's hear it.
If
Okay,
you,
okay.
if you confirm,
All right,
I'll
go.
always just.
I'll go negative infinity to 0, and then 0 to
Well done. Everybody hear that from Brad?
No.
And you can confirm because you're looking at the graph. Say it again, Brad.
let's go negative infinity to 0,
Mm-hmm.
and then infinity, or 0 to infinity.
Okay, so second part of the question then is, at 0, are those brackets or parentheses?
Brackets. Yeah, parentheses, that's what I said.
Yeah, that's what I thought you said. I'm getting old, I have trouble hearing. Parentheses, why would they be parentheses in interval notation?
Yeah,
It's not included.
There you go, good, good. What about, almost done here, part C, Brad?
Where's that?
Well, I'm about to tell you. It's up here. At the infinity and the negative infinity, are those parentheses or brackets?
Those should be brackets.
I'm sorry, again, my ears are bad. Could you say
Parentheses.
Parentheses, very good, that's what I thought you said. The bonus question then would be, before I leave you alone, is why are they parentheses? For infinity.
Calculus.
Excellent. Eloquent students actually learn calculus, correct. Anybody else? Why is infinity parentheses?
Because you never reach infinity.
Correct, we can never reach infinity. It's the whole count dots points thing. Okay. Composite functions. Now you seem to remember a composite function, simply stated, put one function inside another function. You remember doing this, right?
Yeah.
These guys?
Yes, I like these.
Why?
Excellent. The best part is I have it recorded for prosperity's sake of Brent saying he loves these. What is that?
Oh, end of the day.
They're leaving. Where are you guys going? Lunch? Are you going to lunch? Yeah. Okay, thank you.
Wait.
He was like pissed off. I asked him where he was going. Cops have attitude about going to lunch. All right, so let's look in the blue box. If it's in a blue box, it must be important. That's all the fancy calculus speak about what a composite function is. Simplistic terms, you put a function into another function. But look at the notation in the top row.
Today it's already
F of g of x is much different than f times g of x. Okay, f times g of x is just a multiplication of two functions. F of g of x is the same thing as taking g of x and plugging it into that.
Yes.
And you've done a whole bunch of these. Now what gets interesting, and I'm using the term interesting loosely, is trying to calculate the domain and range of composite functions. We'll worry about that later. For now, I just want to be able to come up with these composite functions. So, for instance, I have two functions. Campbell, what can you tell me about f of x? Good start. What else? What kind of function? And don't say calculus.
The slope is 2.
Good. What else?
So y intercept
Good. And what is it? Good. It's a line. Outstanding. Maria, what can you tell me about g of x?
it's trig.
Sorry, I forgot. This Maria. How are we going to handle that? I don't care. Do you want to change your name?
No,
Can I call you George?
Sure.
Okay, George. What can you tell me about g of x?
It's cosine. Cosine is
Very, very good.
cosine.
Excellent. Uh-huh. I understand. Well, there's not much to say about cosine. It's just a cosine function. Okay. So, Nikolai, what's f of g?
Substitute g in for what cosine equals to. So two cosine x minus 3.
That?
Yeah.
Outstanding. Assuming he's correct. Is he correct?
Yep.
Well done. Let's keep this party train rolling. What's g of f?
Same thing, but you just substitute. You put cosine, then 2x minus 3.
Well done. Okay. Good. Easy peasy, yeah?
Yep.
What's the domain of f of x? All real numbers. What's the domain of g of x?
0 to infinity. Or
All reals. Cosine goes on forever in both directions. What happens when you put them together? What's the domain of this puppy? All reals. What's the domain of this puppy? No problems. We're good to go. And I kind of stacked the deck there because I gave you two functions that had their domains being all reals. That will change when one of them isn't all reals. Right now, I'm more concerned about whether or not you can produce these composite functions, which it sounds like you'll be good to go. Now the fun part. So we talked about this a little bit the other day, and that is the graph of the absolute value of x. We all know that we get that v thing, yes? And we talked about why we get the v thing. And that wasn't very exciting. But what will be exciting is what happens if we want to graph that, but we do that.
What were you asking?
Oh, I'm asking. That wasn't rhetorical. Any ideas? Correct. So, all right, let's check it out. Graph the function on your calculator with the absolute value. Calculator or decimal, either one.
How do you put the absolute value in the calculator?
You got
How do you do that?
it. You write a K for your 84.
You might do.
Oh, great question. So Danny just asked a question, how do I get to the absolute value on the calculator? What I do is I go down to the catalog, I'm yelling in your ear, I'm sorry, which is above the 0, And ABS, which is absolute value, is the first choice in the catalog. I think that's the easiest way to do it. You can also get to it through a math menu or something. I don't even know where to find it. Okay, so the question is, where does that come from? So yours should look something like this, depending on if you're a Desmos, how you stretched it or scrunched it left or right.
That makes sense.
How did I get that? Andrew?
Because it's just the normal parabola, but the value's less, the y value is less than 0 reflected over the x or y axis.
Couldn't have said it better myself. I did type it up, though. It looks like that. Okay. If you're taking the absolute value of any function, you graph the function, whatever's below the x-axis, flip it up on top. So this idea allows us to delve a little bit deeper into why is the absolute value of x of v. So when we talked about it the other day, your answers were solid. You can't have a negative x value. But now that we've talked about the absolute value effect, I'm going to suggest another idea, and that is, what does the graph of y equals x look like? Well, you know that the graph of y equals x looks like a line, a 45-degree angle line. Now knowing the absolute value effect, what will the absolute value of x do to it? It'll take this stuff on the bottom and flip it up on top. And that's why the absolute value of x is a v. And which is why the absolute value of x squared plus 3x minus 4 is that parabola with the bottom of it flipped over on top. If there's nothing below the x-axis, then it doesn't affect the graph at all. So if I had something like, let's go with g of x. G of x is equal to the absolute value of x squared plus 2. The absolute value does absolutely nothing to the function because you can never spit out a negative number in that function. X squared plus 2 is always positive. Doesn't matter what you put into it. Okay? Problems, questions? We're good to go? Okay, almost done. You love exponential functions, don't you? Remember that number e? You worked with it last year, right?
No.
Yes, you did.
Yeah, we
Liar,
did.
liar, pants on fire.
It's in the natural.
Okay, so we're going to talk about the value of e. We're going to talk about the graph of e, and we're going to refresh your memory on the laws of exponents. We're going to go through this quickly because I know you learned it really well last year. Does anybody have a $20 bill I can borrow? I will give it back, I promise. No, we got one of these.
Yeah.
Thank you, Luke. I'm glad you're here. This is a $20 bill. This that I'm about to show you is extremely nerdy, but I think you're going to like it. If nothing else, it'll make it almost impossible to forget what the value of E is. Who's on the $20 bill?
Jackson.
By the way, that's a $20 bill. Okay? Who is it? It's Jackson. What president was he?
17.
He was the 7th. What year was he elected? Say again?
1822.
Very close.
It was 24.
1828. Not bad though. I've had people say like 1941. You know. By the way, in case you didn't know, if you're not up on your history facts, Jackson ran for 2 terms. Okay. Hold on, I have to do some more counting. Now, if I take this $20 bill,
Oh, you might have to go to the bank and get a new one.
Yeah.
basically these big sausage fingers, I actually do this. I do some origami and I end up with one of these. What is that?
Triangle.
What kind of triangle?
Football.
Isosceles. Right triangle, also known as a 45, 90, 45 triangle. That is the number e. If you don't believe me, type it into your calculator. The calculator won't show all the numbers, but that is e to about, what is that, 3, 6, 9, 12, 15 decimal places. That serves absolutely no purpose. It's just dorky mathematical.
How did you learn that?
It's part of the initiation to become a math teacher. That is the
You
brand.
have to restate 15 digits.
Yes. Yeah. In a darkened room, blindfolded,
Wow.
where all the other math teachers are in dark robes. It's very scary.
Were you able to pass it the first time?
No, I cried. Yeah, they had to take me out of there. It took me 3 tries.
Wow.
Yeah.
So can you do it now?
Do what now? Cry? Sure, I cry in a heartbeat. Ready? Hold it. No, I can't. I'm too happy about math right now to cry. I'm sorry. All right. Well, that was fun. Hey, what's E?
2.712.
2718.
That was my fault. Okay. Where does the number E come from? Calculus. Very good.
Natural log.
Anybody know, actually? No? Luke?
Inverse of natural log.
Is it?
Yes. I'll give you 85% credit on that. It's much more in-depth calculus, which we'll get to later. But for the most part, it's the inverse of the natural log. So then the question would be, well, where does the natural log come from? And then you can say, well, it's the inverse of E. Well, then which came first, the chicken or the egg? So calculus-wise, we'll be able to explain where E came from. I don't know, what do they tell you in pre-calculus, this number E?
They don't.
They don't say anything about it, just here's E, go crazy?
Basically.
Right?
Grab it a couple of times.
Awesome. So graphing it shouldn't be an issue, right? You all know what that looks like?
No.
Yeah,
I
you
think
can
I have a
see
picture of it
that.
somewhere. No, I don't. I don't have a picture of it. I'll draw a picture of it. It's an exponential function.
Hey, this says it's 182846.
They rounded.
Yeah. Okay, so that's what E looks like. What is special about this point?
Is the values.
Good. And? Do you know the value? No. Not that point.
1.
Correct. Why?
Because e to the first, or e to the 0 would be 1.
Right. Remember, E is 2.7 blah, blah, blah. So E, if you graph it, would be e to the x. And if x is 0, that exponent becomes 1. Question?
How many digits do you want us to memorize e up to? Like,
You don't have to memorize anything. Very seldomly, if ever, will I ask you to memorize things. Okay.
you have to know what a function is. We have to memorize that.
No, that's something you're going to learn.
The entire
If you don't already know it.
test.
Yeah.
Nice try.
The last question.
Okay, so E's kind of fun. Yeah, it's about 2.7 raised to the x power. But what about
21%.
this? How would 2 to the x compare to 2.7 to the x? Would it be steeper or shallower? Shallower? Do you all agree? So if what you're saying is correct, Maria, it should do this.
I think, because 2.7 is greater than 2, so if you square it, it's gonna be greater. And so 2.7 squared is gonna be more than 4. So, yes. I stand by what I said.
That's what you're going with.
Yeah.
Which would then mean, if you stay with that logic, what would 3 to the x look like? Okay, that's going to work really well on the audio recording.
Okay, it'll be steeper.
Good. And you are correct. Yes. When the base of the exponent gets bigger, the graph gets steeper for exactly the reason she explained. It's a bigger number. We're going to focus mainly on e to the x. Yeah. But there are a whole bunch of them
Wonderful.
in the exponents thing. Now this is algebra 1. And the only reason I included this is because people, even in calculus, struggle with the difference between x squared times x cubed versus x squared raised to the third power. What I mean by that is the difference between number 3 and number 3 up here in the box and number 3 down here in the examples. A power raised to a power is multiplied. Two bases multiplied together, you add the exponents. Division is subtraction, and then the last one, number 4, is distribution, if you will, for lack of a better term. And again, I hope you did that already. Yes? So we're done. Let me stop this.